Hi rabbits, Research Turtle here. Today, we are diving into the most significant shift in computation since the silicon transistor. We are moving from theoretical physics to industrial reality. Welcome to the quantum threshold. For decades, we've relied on Moore's law. But we've hit a wall, the silicon wall. Transistors are now approaching the atomic scale, leading to uncontrollable quantum tunneling and skyrocketing energy consumption. We don't just need a faster processor, we need a completely new physics. Enter the qubit. While a classical bit is stuck being either a 0 or a 1, like a coin resting on heads or tails, a qubit exists in superposition. It's the coin spinning in midair. Here's the mind-blowing part. If you have just 256 perfect qubits, you can represent more states simultaneously than there are atoms in the entire observable universe. But one qubit isn't enough. We need them to work together through entanglement. This links data across space, making the system act as one massive organic unit. Then we use interference to amplify the correct answer and cancel out the wrong ones, like noise-canceling headphones for data. So, what can we do with this? First, Shor's algorithm. It threatens current RSA encryption by factoring large numbers in polynomial time. Second, Grover's algorithm. It offers a quadratic speedup for searching unstructured data. It's like finding a needle in a haystack instantly. Right now, we're seeing a Cambrian explosion of hardware. Architects are betting on different laws of physics. We have superconducting loops, trapped ions, neutral atoms, and photonics. It's a race to see who wins. Leading the pack are IBM and Google with superconducting qubits. These are the speed demons, fast and manufacturable, but they're fragile and require massive fridges to keep them at 15 millikelvin, colder than deep space. On the other side, we have nature's perfect qubits, ions and atoms. Companies like IonQ and QuEra use lasers to trap individual atoms. In 2024, QuEra achieved a massive breakthrough with 99.4% fidelity using magic state distillation. These systems are naturally identical and hold information longer. The biggest enemy, decoherence. Heat, vibration, and radiation kill qubits. Our goal is to keep them alive long enough to compute. And that brings us to the present. 2025 is the era of fault tolerance. Google's Willow chip and Microsoft have proven that we can use many unreliable physical qubits to create one reliable logical qubit. As we scale up, error rates are finally going down. We have crossed the break-even point. We're even solving the hardware issues. Look at this wiring mess on the left. The solution is Cryo-CMOS. Companies like Samsung and Intel are building control chips that sit inside the fridge at 4 Kelvin. This solves the I/O crisis. The industry revolution has begun. In finance, Goldman Sachs is moving from overnight simulations to real-time risk analysis. In security, JP Morgan is preparing for the post-quantum era, securing blockchain networks against future threats. In science, we're simulating nature with nature. Roche is looking at Alzheimer's research. Hyundai is analyzing lithium compounds for better batteries. This isn't just theory, it's happening now. This is also a battle of sovereignty. The US, EU, and China are investing billions. South Korea has launched the K-Quantum strategy, aiming for a 1,000-qubit indigenous computer by the early 2030s, with players like SK Telecom and Samsung. The science experiment is over. The era of engineering utility has begun. The question is no longer if, but how fast. We are witnessing the dawn of the fault tolerance era. That's it for today. Turtle out.